Okay, going now to the last part of our discussion on force and motion. Let's have a couple of more examples. Sample problem number 3. You have a bust of mass 5 kilograms suspended by 3 strings as shown here in the figure. And you have 3 strings, so let the left one be string 1, the middle one be string 2, and the right one be string 3. So you have a bust suspended by string 1, string 2, string 3. String 2 is vertical, string 1 is 45 degrees to the right of y-axis, to the left rather of y-axis, and string 3 is 45 degrees to the right of the y-axis. The tension in the left string is 23.1 newtons. Determine the tension in the middle string. So, string 1, tension ay 23.1 newton. So, T1 is equal to 23.1 newton. String 2, we are asked to get the tension in string 2. So, T2, we are looking for. Mass of the object, the bust is given 5 kilograms. If we know the mass, we know the weight of the object and vice versa. So, mass is 5 kilogram, the weight magnitude is just mg, which will give you 49 newtons. We are already provided the drawing of the system. So, identify now the forces present in the system. The bust has mass, automatically it has weight heading downward. And because of the weight, the 3 strings are being stretched. The strings will react by pulling at the endpoints. As far as the object is concerned, there are 3 tension that are pulling it upward. You have tension T1, T2, and T3. One for each of the 3 strings that we have in our system. The bust, the object is simply hanging, suspended. It is static. You have static equilibrium. F net is equal to 0. F net is summation of all the forces acting on the system. So you have weight plus T1 plus T2 plus T3. Using now our component method to analyze the free body diagram, the forces, X component, F net, X component of F net, you have F net X. F component of 0 is 0. X component of the weight, vertical, no Y component. T1 is diagonal, 45 degrees. The X component is negative direction, opposite of 45 degrees. So, negative direction, T1 sine 45 degrees. So again, use your SOHCAHTOA to divide the vectors into components. X component of T2, T2 is vertical, so no X component. X component of T3, T3 is diagonal. X component, the horizontal component, is heading in the positive direction. And it is opposite the angle 45 degrees. So we use sine 45. And again, positive direction. So plus T3 sine 45. The X component tells us that the magnitude of T3 is just the same as the magnitude of T1. And we know T1 to be 23.1 Newton. So we got an answer for the X component, but it is not what we are looking for. What we are looking for is T2. So we move on to the Y component. Y component of 0 is 0. Y component of weight. Weight is vertical. All of it is in the Y component, negative direction. So negative W. Y component of T1. T1 diagonal. The vertical component is positive direction, adjacent to 45 degrees. So, positive T1, adjacent. So, cosine 45 degrees. T2 is vertical. All of it is in the Y component, positive direction. And T3 is diagonal. The vertical component is positive direction, adjacent to 45 degrees. So, adjacent, you use cosine 45, positive Y direction. So, plus T3 cosine 45. T3 is just the same as T1. So, we can replace T1 by T3 by T1. So, you have 0 is negative weight plus T1 cosine 45 plus T2 plus T1 cosine 45. Simplifying, we have T2 is equal to W minus 2T1 cosine 45. We know W. We know T1. W, 49 newtons. T1, 23 newtons. Plotting in the values, we are able to calculate the tension T2, the tension in the middle string, 16.332 newtons. Next, we have the following example. Sample problem 3. You have a diagram of a box sliding at 3 meters per second. Initially, the surface of the floor is slippery, so we can consider it to be frictionless. But it encounters a rough patch on the floor. So on this rough patch on the floor, there will be friction between the box and the floor. The coefficient of kinetic friction between the box and the rough patch on the floor is 0.5. Determine how far the box will travel before coming to a stop. Since there is now friction, kinetic friction will try to stop or slow down the object while it is sliding. Eventually, the object will come to a stop. How far will the object travel before coming to a stop? The mass of the object, mass of the box, is 1.5 kilograms. So, given M is 1.5 kilograms, knowing M, we can calculate the weight magnitude of the box, 14.7 newtons. Coefficient of kinetic friction is given at 0.5. And the initial speed of the box, when it starts moving on the rough patch, the initial speed of the box is 3 meters per second. And according to the diagram, positive direction. According to the figure provided by the problem, the box is sliding to the right, so V is positive, V naught is positive direction. The box comes to a stop, so the final velocity is 0. We are looking for how far will the box travel, so magnitude of the displacement. or distance traveled x. We have a drawing of the system. So, identify the forces present in the system. The box has mass, so it has weight vertically downwards. Because of the weight, the box is pressing into the horizontal floor. The floor will produce normal force in reaction to the box pressing into it. So you have weight, downward, normal force, upward. The box is going to slide to the right. Kinetic friction will oppose that, so kinetic friction will be heading to the left. Since the box will eventually come to a stop, the object is undergoing deceleration. And when you have deceleration, the acceleration is heading in the opposite direction as the motion. The motion is heading to the right. The acceleration is heading to the left. Deceleration. Since there is acceleration, you have an accelerating system. F net is equal to ma. F net is summation of the forces acting on the system. You have weight, normal force, and friction. X component, F net x is equal to x component of acceleration. Acceleration is horizontal, negative direction, so minus ma. X component of weight, vertical, no x component. Normal force, vertical, no x component. X component of kinetic friction is horizontal, negative direction, which tells us that ma is just equal to kinetic friction magnitude. Ma is just equal to Fk. There you go. Ma is just equal to Fk, kinetic friction magnitude, and we know the magnitude of kinetic friction is constant at mu k n. Isolating A is equal to mu k n over m. We know mu k, we know m, but we don't know the normal force magnitude, so we move on to the y component. Y component of F net is F net y. Y component of MA is horizontal, so no y component. Y component of weight, vertical. All of it is in the y component, negative direction. Normal force is all of it is vertical. All of it is in the y component, positive direction. And Fk, kinetic friction, is horizontal, no y component. So, negative weight plus n plus 0. The y component tells us that the normal force magnitude is just equal to the weight magnitude. So, A now becomes equal to mu kW over m. And we know the weight of the object because we know the mass of the object. So, plotting in the values, we get A to be equal to 4.9 meters per second squared. So, the magnitude of the acceleration of the system is given by 4.9 meters per second squared. But the acceleration vector is heading in the negative direction. So, when we convert this back to a vector, when we convert this back into vector form, vector A is equal to negative 4.9 meters per second squared. Because negative direction. And knowing the acceleration will allow us to perform kinematics analysis on the system, on the box. The acceleration is constant at negative 4.9 meters per second squared. So that's uniform acceleration. For uniform acceleration, you have 4 equations that you can use to analyze the motion of the object, of the box. One equation is v squared is equal to v naught squared plus 2ax. We know final velocity v, 0. We know v naught, 3. We know a, we just calculated a, negative 4.9. We don't know x, so variable x. The only unknown is x. We are able to calculate x to be 0.918 meters. This example illustrates how force analysis may be combined with kinematics analysis. In this particular example, we performed force analysis first, and then we did kinematics analysis. But in other problems, it might be the reverse. You might be required to do kinematics analysis first, and once you have the acceleration, that's when you do force analysis. So be prepared to do both. Be prepared to combine your force analysis with kinematics. And that's it for our discussion for this session. And that's it for our discussion of the topic of force and motion. So thank you for watching.